Christian, du bist bei uns in einem der Teams im Kontext der Auffindbarkeit, in einem Team, das sich konzentriert auf die Entwicklung einer semantischen Suche. Und dazu wirst du uns heute ein bisschen was berichten. Wir sind sehr gespannt. Viel Vergnügen.
Yeah. Thanks for the brief introduction. I speak in English. That's the OTTO style. We have English native speakers giving you talks in German, and then we have the native Germans being asked to speak in English. So welcome to an English talk. My name, as Timo said, is Christian Haase. I'm a member of OTTO's team touring, and they're all here in the front row. So a little applause. So yay, that's the team. Basically, I'm presenting our team's results on the development of semantic search for low recall segments. And it really fits well to the previous talks. As you will see, we also used Domäneneinschränkung very strongly and denoising techniques to actually get in the low recall segments our semantic search going. It also ties, I'm also a member of the language technology group at the University of Hamburg, and some of the aspects sort of tie in also with my research on semantic clustering. What will be this talk about? First, I will explain to you what does OTTO's semantic search system actually do. Then we go a little deep dive into the challenges. What kind of issues or challenges did our previous models face? Then how did we solve them with our great team? And then sort of also go into a wider discussion, looking at our solution, which is very query-centric. What we can learn from this about the whole development of semantic product search over the last 2 and 3 years. And in the last year in particular, as will be explained later, we've seen many new innovations in that direction. And so at OTTO, we're trying to push certain ideas for low recall segments, which are also sort of pushed by Amazon and other big players. And that then brings me to the conclusion. So let's start. The introduction is semantic search system. What does it do? There are 2 main ways of matching products and queries. One is the lexical way, and the other one is the semantic way. One, you look out for the exact spelling. The other one, you look out for the similarity of meaning. That's sort of a big difference. OTTO has 2 systems in place, and they're working in parallel in a hybrid search architecture. One is the spelling-based equality checking for the same spelling, the SOLAR system, and the other one is our system, which works on the more low recall segment end of the search distribution, which is the semantic system. The main problem of a spelling-based system, as the name already says, is that it cannot really understand very well spelling errors. You can help the SOLAR a bit, but at the end of the day, it just falls flat. It doesn't understand if someone types in. For example, here I brought an example. That's what our customers very often actually type in is iPhone Pro Max. So as you can see, that's not a standard spelling. It's a variation, A-I-F-O-N, and then just one word, Pro Max 13. That actually happens quite often. So a keyword system like the SOLAR, which knows, ooh, I've got a product like iPhone 13, falls flat, doesn't understand it, and comes up with something which we call 0 hits. And at the last main, our team already, or the previous team, presented a solution for that. And then the semantic search system kicks in, which now can learn from our data that spelling variations, such as the very unusual iPhone 13 Max, equals actually iPhone 13, and that's our current system, and it actually displays iPhones. So that's the whole thing, what we expect from the requirement the system to do if it works really well. However, to make these systems work really well and to really match really unusual spellings and semantics and synonyms, it's really, really difficult. So that's what our previous system, which was in operation until June, did. Here's the first quiz. The customer enters Duxer Matur. Anyone an idea what the customer really wanted? Yes? Yes, a Duscharmatur. Our previous system thought the customer wanted a Hundekostüm. Why on earth in our Hundekostüm, which we offer at OTTO, there's a cat in a Princess Leia dress? I don't know. Which is on the left. I actually brought this red light to show this. Oh, yeah, very nice. Here's the cat in the red Leia dress. Okay, the next one. we always had these sort of test cases. A Ventilator, anyone? What that may mean? Ventilator, right, correct. So what did our previous system thought? It thought it was some sort of card game, the Ventilator. Okay, so these are the challenges that you face on a daily basis at OTTO, and it's always quite funny when we go through these cases about Hundekostüme. Just to be very brief, so that's a summary what the new system, we expected the new system to do. We basically said, okay, it needs to recognize that a Ventilator is actually a ventilator. Eventually, we managed to train the system to learn this, to find additional ventilators. And so the steps that you will see, what's new about our system, it marries really two approaches. One is called query understanding. So it understands that something like Ventilator means ventilator, and then it also retrieves ventilators. So it's a bit of that's a semantic search system, because then can understand, this is the correct product. So it's two steps being involved, and you will see there are two main modules doing the job. The new system has also an additional trick. That's the real trick, and I'm quite proud of it, because if you're familiar with search, we're talking about head and tail queries. So a head query like iPhone, you find 10,000 products. It's easy to resolve, yeah, because you've got enough data. It becomes really problematic if you're looking at tail queries, where one product, one query, one product being found by the Solr. Once it was clicked, you have not much data to learn this. And the new system is actually able to aggregate tail queries and tail product data and matching tail product data through a clustering trick, which I will be explaining later. And that's why we can find something. For example, here we have an example. If you enter something like Fred Perry, you end on the tail. It's actually quite a popular brand. But due to COVID production issues, we only have 3 products on offer. So you used to have like thousands of products, but these days, there are no polo shirts, for example. That's the main product of Fred Perry. So what can you do? And we actually trained the system to look on the tail for similar products, which is a bit difficult and tricky. And that's what the system does. So again, an ideal outcome, it actually finds a polo shirt from a different brand and offers it. So that's these are the two tricks, or the two problems we needed to solve, really. In essence, the new system is really specialized for problems in low recall, and the underlying assumption is always, and that's why we call them low recall, there are more products, more relevant products available on the tail than the lexical system retrieves. More relevant products. That's why we call it low recall. The lexical system doesn't recall all relevant products, and that's the conditio sine qua non. If there are no more relevant products, we wouldn't need to have a machine learning system. We need to find something, and we need to ascertain through tests that there are relevant additional data. That's basically the brief introduction. How does a semantic search system work? That's something we need to understand just to see the challenges that we resolved. The basis of a semantic search system are click data of any semantic search system. You have a catalog, the customer enters iPhone, you display iPhones, the customer clicks on an iPhone. And that's how the system learns it. The query, that means that what was clicked. That's the basis. And if you sort of aggregate these query and click products over time, so someone enters iPhone today, someone iPhone tomorrow, clicks a 12 Pro Max, 13 Pro Max, you get a graph, a very basic bipartite graph, as it's called. So you can always have an edge between a query and a product, and you had a positive signal. The whole idea of semantic search is to cluster that graph, sort of if you visualize it as a graph, and to find additional products in that cluster. For example, for that query, it would be, if that's the cluster, you would, for that query, perhaps in your aggregation, find product 1 and product 2, but product 3 would be really, that's what you want. That's the additional relevant product in the cluster, and that's the gold you want to retrieve. And you don't want product 4, because that's out of your cluster. So you need to take really precautions that you don't find product 4. It could be very, very similar. It could be named iPhone, Hülle für den HSV or something, but the customers didn't want it. So you need to have your decision boundaries for your models later on. And these are all based on these clusters, basically. Now, we had a number of implementations and of this graph in various ways. So one implementation is, for example, for our former low hit segment, which is defined by 1 to 16 products, a team is a really great idea. Just take this graph and look up the product that was clicked. So we display a green shirt. Then the system goes to the graph, looks, ooh, here's the green shirt, takes 2 hops over the graph, like this, and you go back here, and basically then finds another product. The problem with that system was that if you only walk on this graph, you don't really have the cluster. And there can be problems with the graph. Edges can be missing, etc., etc. So that was the main problem, where the system stayed very close to actually what it found. So it had a green shirt here, and then it found a blue shirt. That's the old system, which you can imagine, okay, went green shirt, oops, blue shirt. Then it had a shoe, and then went, oops, a shoe, and it found another shoe. Another black shoe, but the polo shirts are missing, and you see sort of the system somehow misses parts of that wider cluster and the wider aggregation. So that was one of the problems with the previous system. But it was sort of a great idea because the graph is really at the center. Then we had the second system, which was introduced last year at the main conference. That's already a bit more advanced in a way because it uses that graph at the center, here again, but it uses it from a query side. So it takes a query. Oh, have I seen a similar query? And then it retrieves the products to it. It also has introduced a zero-hit solution. So queries with no clicked products were also inserted into the graph, basically through session aggregation. And in order to resolve that and to get on the graph, we had a language model. So customer enters something like iPhone 13 Max. Then the language model says, ooh, do I know a similar query on the graph which really fits that? And then it sort of says, ooh, here are 5 queries. Then it takes the products from this graph and recommends them. And that worked already quite well. That was quite a good system. But again, it had a bit of problems in finding these clustered products because it didn't really use any clusters. And the language model, and here we relate to our previous 2 talks, had really problems in denoising errors. And that's what you see in the Duxarmatur to Hundekostüm, because that BERT model here on top was a bit stupid. It just didn't get it. Because obviously there were several issues. It wasn't really pre-trained for that, etc., etc. But it had a number of issues. So, but that was the previous system. But the basic idea was already quite good, and it also sort of displayed a wide variety of products. So, and then we had a third system, a test system, and that's what you probably all have heard about and known better or know better than our 2 more graph-based systems is sort of a sentence BERT. Yeah, sort of a standard system. You take a BERT model, you put a sentence in, you aggregate all the vectors, then you learn them by click data. You push the semantics so they fit the click data, and then you generalize that and use it. That's a standard system. However, if you look at the graph, this system had problems on the tail because, like all the other systems, it couldn't really find the clusters, it couldn't generalize well because the graph on the tail has all these missing edges. And the BERT system learns the edges. That's what you enter into a sentence BERT for training. You say, oh, here's a product, here's a query. That's basically the edges on the graph. Learn that relationship and change the semantics in the model to fit that learned relationship. Customer enters iPhone, R-E-F-O-N, but you should learn it means iPhone as a product. And the system wasn't able to learn that for tail products, basically, because it is so difficult, because we have a broken graph. So that was one of the problems. So now our solution. We looked at the systems we have, and great work from all the teams before. Everything was tested when we started our project. That's the Semantic Spike project in April. And we said, okay, The solution 2 looks quite cool, actually. Sort of it finds products. It's a differentiated module. It's not the standard bird, so we tested that as well. But we look at this. And what do we need to do? Basically, we need to solve the clustering issue, because obviously the graph had problems with missing edges on the tail. And we need to improve the generalization capabilities of the language model. And the tricks you will see relate really to the previous talks, Domain-Einschränkung and a better, more robust language model. Then we tested that, and today we use it in low recall segments, and I will show that. You can go on the page otto.de, I can give you some queries, and you can see that in operation. Okay, let's look at our solution in more detail, and then what we learned from that in more general. The solution. As I said, it has sort of two main parts. We had two main problems, denoising and cluster part matching. So the first part is that the unseen query comes in, we assume it is a distorted query, and we denoise it to k denoise similar queries, so k and n vector search. We say these are the similar queries that we know, and we aggregate about 6 million queries for that. So that's really a good distribution of what our customers want from us, and we cover really nearly everything with it. And the second system is a bit of a trick. It uses the cluster part aggregation on the tail, which I'll explain in more detail in a second. And then we do some further filtering and ranking, and that's it. So the core requirement to actually build that system was a robust and precise language model, which could understand the queries in the first place. And that's really the key to it. So that's the key requirement. And with that, now comes the trick. It's the first time I talk about the trick. Never revealed before. Here's the trick. Even my team doesn't really fully know it. It's a surprise for you as well. Here's the trick. That is, if you have a model which is very robust to errors and variations, you can use it to make a tail aggregation of cluster parts. Because on the tail, due to the missing information, it was only once clicked, your problem is that you're missing edges in the graph that you can learn with the model. So you need something to basically collect all these cluster parts on the tail together, which in other cases, if you had had the ideal distribution of edges, would have formed a cluster. But they never did that. And so you can use this model, and if that is our tail graph, and here you have the ideal cluster, so the red dots, that's the ideal cluster. And you have second ideal cluster. So that's really the iPhone cluster. So that's the example. That would be the query iPhone 12, another iPhone 12, 500, whatever, GB, and another iPhone. And here you have iPhone, whatever. It doesn't aggregate because you don't have enough data. So you use that similarity between the queries to aggregate these cluster parts on the tail. And that's the whole thing what the model does. So it's very sensitive to spelling variations. And then we use that to basically rake the gold from the tail. And so the hypothesis is that the queries of tail clusters and cluster parts from that query product click distribution exhibit a high degree of semantic similarity, and thus can be aggregated by a list of k nearest neighboring queries if and only if the model is really sensitive to spelling errors and variations. If you have an untrained BERT model, it just goes boom somewhere else. So it will never find the relevant parts. So that's the idea behind that. We also checked that, but I skipped that. Let's stick with the language model. Then we needed to design a language model which could really understand all these all these funny variations and really understand that there's iPhone is iPhone. And what we found is that Roberta and BERT tokenizers, and they're known in the literature to exhibit problems, weren't really up to the job because they split the words into basically semantically, statistically optimized subwords. That's so a Schuhe would be split into Schuh and an Endungs-E. I tell that in German because I don't know what it means in English, an Endungs-E. So that would be an ideal thing. Then it could learn that the language model splits all the words in a sentence like this. Then it learns the semantic that a shoe is something now you wear, etc. It has sort of other meanings, synonyms. It learns that on top of these tokens, these subwords. BERT does that. And it really piles it up. And if you look at GPT-3, etc., they only use 30,000 tokens. So the more semantic the language model learns, the less number of tokens it actually can use because it just piles it all on these subwords. The problem is, with that approach, that it becomes not robust to errors, because if your tokens change or if you have a random insertion of a character inside the token, the model is off. It doesn't understand the semantic, it doesn't understand the word, it's off. And that's why it is in the literature known that you have problems with BERT tokenizers. So we changed to Roberta, which BERT only uses 30,000, and we tried Roberta, which is an order of a magnitude up, 250,000. Still had no real good results. Because if you have, as I said, here's the example, Schuhe-weiß, sort of the H is missing and the I is missing. You have 2 words, 2 errors, and then you only have a match of 25%. So that's not very good. So what we did, we went up by another order of magnitude, and we said, okay, 250,000, let's take 2.5 million tokens then, which is pretty hefty. And we limited the text the model was learning, so our Domänezentrierung, to only the queries. So we spent like these 2.5 million tokens, and we couldn't do that with BERT very easily, so we used fast text. I don't know, it's an older model, but which is very easy to tweak. And so we used that to learn these tokens, and also we decreased the token size. So we set this to 2 to 3 char n-grams, so character n-grams. The standard BERT model, very often, you can go for standard lengths of tokens. Very often they end up with something like 5 or 6 or so. But 2 and 3, the limitation is really low. So very, very slow, very, very small tokens. And you can see the example here. Schuhe-weiß suddenly has this, that's a start sign, SSC, the whole length of tokens representing the word. And then if you insert the same error, you have 7 or 14 tokens matching. So that's much better for error-prone text. So we pre-trained the model on all historical queries, including all zero-hit queries, to increase the robustness of errors and variations. We designed also a specific adversarial test to do that by measuring all the error distributions in our pipeline. So we used that. So there are, if you use edit distance, very heavy errors, so light errors, no errors, 35%, 1 distortion of the word or of the sentence, 19%, 2, 22, 3, 14, 4, and you can go, Duxar Mature has, I think, only 2, so that's only difficult to understand, but there are, you guess it, if there are 11 distortions of the word, it's very, very difficult to understand. And then we used sort of e-commerce specific phrases, separate joint writing, deletion, swaps, additions, and also sort of started playing with synonyms for an e-commerce specific test. And that was our development phase. And here's the A/B test. Then we thought, okay, here we have a clear hypothesis. A, the model now should be sensitive to spelling errors and variations. And because it should be able to aggregate cluster fragments. So it should do well in our 2 low recall segments. One is the so-called low hit segment, where the Solr retrieves 0 hits. And the other segment is the 1 to 16 products. And now, applause. If it hadn't been a good test, I wouldn't be standing here. So that's basically our hypothesis. And then, bam, we had the jackpot, basically, where we had a conversion rate increase of 25% in the zero-hit segment, and a whopping conversion rate increase of 94% in the low-hit segment. So, yeah. We were actually quite pleased with that. And Otto said, thank you very much, you're now a team. So that's why we're all sitting here, basically, because we successfully concluded that project based on these 2 assumptions, which we solved with one sort of really robust language model, and that's why it works. It looks like a strange A/B test, so why should the same model work in two segments, but they're sort of related due to their tail characteristics? Yeah, so that's basically that. Going back to the test, that's actually the Dux-Armatur. It now really thinks it's a Dusche-Armatur, and it now actually also recognizes the ventilator. But however, there's something more than joy at OTTO for our good test results. There's something more fundamental going on here, and that's that we actually pushed the development of the model towards a query-centric solution. So we actually said, okay, the main problem here are the queries, and we need to do something with it. And that's something which, if you look at the history of semantic product search, was perhaps a bit overlooked in the first 2 or 3 years. If you look at sort of the first generation of models like Sentence-BERT, they were heavily product-centric. The model was trained with queries, very often only a tiny bit, and a huge corpus of product titles. So what the model learned was actually the product titles and a bit about the queries. So that's why we call these first generation models really product-centric. You can go on, it's asymmetric, a query is short, the sentence of the product title is long, BERT can deal with the longer sentence much better than with the short thing, etc., etc. So it all was geared or not reflected that it actually sort of neglected the query bit. And if you look at the publications in the last year, you can actually see that many other companies have done similar stuff. So you have sort of, I think that's the ONCE data set. It should be some Home Depot. I think it is from the United States. The authors, Zeng 22, has shown that a query pre-training of a BERT language model can really help you to get better clustering, because it learns that these queries on the cluster belong to each other at the tail end. So that's basically what they actually found out. Also, at the Special Interest Group for IR conference in June, a new robust BERT model has been introduced, so-called with a character BERT, it's called, which is more robust, particular to spelling errors in queries. So that's really a big topic. And Amazon has also added some query-centric clustering to their production system to scale it to 1 billion products. So there's a lot of movement in the sector towards these query-centric and cluster-centric solutions. And basically what we at OTTO found also, for our problem, only for our specialized problem at the long tail, that we had the old solution, the graph, which was product-centric. You remember there was a product graph. That didn't really work well. Then we had a new solution, which was much better already, the old zero-hit solution, but it wasn't really pre-trained on the queries, so it was a bit mixed. And then we found that on that side, we found a new solution, which we were happy with. So it's a shift in the solution space, which you also see in the literature. And that's probably what we're also proud and thought, okay, that's something where we give a talk about. So that's the whole idea here. The implementation is also something, if you use something like fast text over BERT, it is way, way faster. So we're really proud on the implementation. It's an approximation algorithm for finding cluster parts. We're not clustering, no graph thing, just a simple Python dictionary, a simple fast text, and an MSLib library. And so it resolves a query on average in 5 milliseconds. So I think the Amazon system is standardized for resolving queries in less than 20 milliseconds. We're below that. So that's quite cool. And we have these nice dashboards, which our team built, which always show how fast we are. So that's also quite good. So that's something from an engineering perspective where you go, okay, that's simple, that's efficient, solves the problem, and is really fast at the end. Also has, of course, trade-offs. It's not everything is perfect. We overemphasized robustness over semantics at some point because we thought, okay, we have these errors and we need to resolve it. So it also, you can trick the model. For example, if you search for grass sack, it really doesn't know whether you're searching for grass or sack because it sort of has all these sort of small parts, and grass could be an error. So it goes with the thing, and after that finds a Schlafsack, which is something we need to work on. It's a known trade-off of the model, so that's something what we want to improve. Conclusion is basically what we've done sort of in the research field, that we integrated sort of research papers on semantic product search and query understanding. That's sort of the whole basis, a new combination of both. We emphasize this query-centric solution, and it is, of course, applicable for the long tail, so zero-hit segments, high noise, data sparsity segments. If you encounter problems like this, come and talk to us, and we will find a new solution. It really has some new sort of ideas. That's that new approximation algorithm for tail clustering, the semantic similarity of query variations that way through the broken graph. It's an hypothesis, but it seems to work. As a new robust language model, and obviously you've seen also a new form of hyperparameter tuning, and these adversarial tests are also discussed in literature, and we felt often are lacking e-commerce specific, really hard tests, which really occur in our pipeline. If you look at the last paper for character bird, it's like, oh, we just taught that one word sort of with one edit distance, where I went like, look at our pipeline, we've got all these crazy words that never would work. So we're also developing these tests, and they seem to be quite central in making more robust models. And also, it is applicable. And now I look to Johannes over there. We are also both from the University of Hamburg. We haven't cooperated yet, but it is, of course, this high denoising techniques are also applicable to voice search, where you have sort of, Johannes showed it, the statistics, finding the characters and subwords, etc. So I think that really is also something which you see, for example, in the Alexa research, some fast text models which are similar to ours in the way that they denoise their queries sort of in the S1 paper. But Johannes will know more about it, I guess, and probably has a better system as well. So our outlook is these are the next milestones at OTTO for our new model. It is part of a hybrid search architecture. And that needs to be fine-tuned because obviously, I mentioned that on the first slide. I said, the lexical engine Solr can also have some sort of error resolution or synonym resolution. So obviously, that needs to be integrated. That's a challenge we are facing at OTTO, to integrate constantly our machine learning models even better with the Solr, etc. So lots to do. Then we're only returning at the moment 18 products, which is easier than to return more products, because obviously, if that graph aggregation works well, it works better for the first cluster parts you find, and it's getting more difficult. So that's a challenge. We also want to go into our product list. It's currently only working on the search box. When you enter a search box into the OTTO website, you come on the zero hit and low recall segments, and you can see them sort of on the page as well. But there's also a second option. Has anyone ever used that navigation tree on our website? Honestly, I'm interested in that. Is actually anyone still using? Oh, you do. Wow, wonderful. Applause. And you have. Yeah, it has a bit gone out of fashion due to mobile first, because obviously on the mobile you can't use that navigation tree very well. It used to be more popular a couple of years ago, but nonetheless we also want to deploy that module in that space while we're transforming it for low recall product lists. So that's something we're planning. And certainly our research will revolve around clustering and denoising in sort of fulfilling these new objectives for OTTO. Thanks for your attention. And that was the talk about our new low recall architecture. Thanks a lot.
Christian, thanks very much for the interesting talk. We do have time for at least one question, and there are questions online now, but we can take those. And one question is, did you try classic information retrieval approaches like spelling correction of the query, for example, with trigram, Levenstein distance, and query expansion?
Yes, we tried everything. And coming from our NLP team, Deep Sense, that really the SymSpell, that was the spelling correction system we use. We only use it until Levenstein distance of 2. However, there are so many cases. It is actually used in the pipeline, but it can't really deal with sort of harder cases. And there are also other ways to outmaneuver. It is sort of outmaneuvered in our pipeline. For example, if you have some certain 3 keywords match, but the fourth doesn't, then suddenly this error spelling is not used by the Solr and it is returned to us. So there are all kinds of situations where we had the feeling, okay, where this word is positioned in our pipeline, A, it's not as effective as ours, and second, it is positioned in our pipeline at a certain stage where it helps with certain aspects, but not with others. So yes, we tried everything and we felt it wasn't enough.
Okay. We do have time for one more question, although we have several more questions from the audience. The next one would be, do you also look at sequences of search keywords? A user might start with a misspelled query and end up with a more specific or correct.
Oh, yeah. A very important question. I was too short on this, so I thought because Levente explained it last year, but I actually have to admit, people won't remember that much from a talk. Yes, if we go back to the very beginning, that's the idea. That is the aggregation of 0 hits, and they are actually aggregated from a session. So the whole thing about maneuvering this queue into the tree is a session-based aggregation, and what you get is actually the reformulations. So someone will try iPhone with a horrible misspelling, then realize, oops, I've got 0 hits, I didn't get what I wanted, and then try various attempts to get better results. And that's, of course, what we learned from. So there we have various 0-hit queries until the customer. So we learn and we actually connect the products to these previous queries. So it's a sort of a reformulation learning, and with a sort of twist, because we aggregate all reformulations, so all various wordings and spellings of A-I-F-O-N with all kinds of variations, and that put an additional requirement on the model. That's why at the end we felt this can be only resolved with such it's an aggressive denoising model. Sort of for someone working in that field, it is really, we push it to the maximum. So you can't have, if you look at subwords, you can't have less than 2 because otherwise it's called characters. So you can't get lower if you use that architecture. And so that has something to do with the aggregation mechanism behind that, from which we also learn. It's a bit short in here, sorry about that, but it's a very good question because it's somewhere tucked away here that we also do reformulation learning.
Okay. Thank you very much. For the other questions, I would suggest to approach Christian. He will be happily answering those questions later, or maybe you can contact him online.